We started chapter 2 right before the test, and so we talked about some basic operations and basic vocabulary words that we need to be able to use to refer to matrices, and then do stuff with matrices like add and scalar multiply. So this is already up last time, so I'm not going to go through it except maybe highlight a couple of things. Um, We have some basic properties for addition. It's commutative, associative, and all that. It has an identity, and that's called the additive identity. And then for multiplication, it's associative, and it has an identity as well, but it's not commutative. And so that's this warning over here to say that AB is not actually necessarily equal to BA, although there might be some cases where it actually would equal, and then they are called special matrices. And then we talked about the transpose, where we switch the rows and the columns of things. So that was from last time, and this time I want to, well, we could probably take a look at a couple of problems from section 2.1 just to provide some examples and stuff. And let's take a look at number 1 and 2. Maybe not do all of them, but uh-oh, it came up. Hmm. So we probably won't go through all of these, but let's take a look at some of the basics. We have uh, two matrices that are 2 by 3, and we have a couple of 2 by 2s, and then an E matrix looks like a column vector, but we can also say that's a 2 by 1. So knowing the size of the matrix is going to be important for us to be able to combine things. And let's take a look at, out of these examples, let's take a look at things that we won't be able to do. Um, was there one off the top here? Oh, let's take a look at 3c minus e. This is 3c minus e. And the fact that these two matrices, for you to be able to add matrices, add, subtract matrices, they have to have the same size. So this is C and E are not the same size matrix, so we can't combine it. So that's important to be able to combine matrices. You have to have the same size. So something like A plus 2B is something that we can do. So if we take a look at A, 2, 0, minus 1, 4, minus 5, 2, plus 2B, 7, minus 5, 1, 1, negative 4, negative 3. And that is something that we should be able to combine. So I would scalar multiply first. And so that doubles everything inside. And then we can add term by term. We have 2 and 14, that's 16. 0 minus 10 and minus 2 or minus 1 plus 2, and then 4 and 2, 5 and negative 5 and negative 8, 2 and negative 6. So to be able to add matrices, you have to have the matrices to be the same size. So multiplication is a little bit trickier. Let's take a look at A multiplied with C. So A multiplied with C, we have 2, 0, minus 1, 4, negative 5, 2. Multiplied with C, 1, 2, minus 2, 1. Yeah. Yep. Positive 1, right? All right. So to do this multiplication, before we do this multiplication, what we have to do is we have to make sure that they're of the right size. And so this is a 2 by 3, and this is a 2 by 2. And the thing about this is that when we do the multiplication, what we need to do is we need to multiply. How did they define multiplication? I don't know exactly how they define multiplication, but the way we're going to look at it is we need to multiply the vectors 2, 0, negative 1 with 1, negative 2. And it turns out that for something like this, they're not compatible. You're not going to be able to multiply these two matrices. Yeah, if it was a 3 by 2. Or even if we do it this way, C times A, if we switch the order, and we got 1, 2, minus 2, 1, and 2, 0, minus 1, 4, minus 5, 2. And we could take a look at multiplying a couple of vectors element by element here. That would give us 1 times 2 plus 2 times 4. And that would give us our first element here. And then we would, I don't know how to do this. Now it looks like it's green highlighted. And then you would take these two vectors, 1 times 0 plus 2 times negative 5. And then you would take these two vectors, 1 times negative 1 plus 2 times 2. And then that would give you the first row of your matrix. And then you would do the same thing for the second row and each of these columns. So the multiplication here would be 2, negative 2 times 2 plus 1 times 4. And then we'll do the same thing minus 2 times 0 plus 1 times minus 5. And then minus 2 times negative 1 plus 1 times positive 2. So the resulting matrix that you would have in this multiplication is whatever this turns out to be. So this is 2 plus 8, 0 minus 10, negative 1 plus 4, negative 4 plus 4, 0 minus 5, and positive 2 plus 2. So the quick way to check if you can multiply a couple of matrices is to look at their dimensions. And that the number of rows for the first matrix has to match the number of columns for the second matrix. And if they do match, then you can perform the multiplication, and then your result will be the number of rows in the first matrix and the number of columns in the second matrix. So, how many people have done matrix multiplication before? All right. So that's a general idea behind matrix multiplication, and we want to just be able to practice a bunch of these things so that we can get used to it. And then when I do this, I'll try to go a little bit quicker than doing all these steps. Well, it's not too arbitrary. According to, maybe I didn't put it here. Well, the matrix multiplication is really a series of dot products or inner products. And we're taking the inner product or the dot product of rows in the first matrix and columns in the second matrix. And that's how they do the multiplication. Okay? I don't know if we need to do anything else. So that's the general idea behind these matrix multiplication things. So let's move on to the next section where we're actually going to do inverses. So this first one, the first section in this chapter is really just a bunch of algebra that you need to get used to. And matrix algebra is just a bunch of computations. And so I encourage you to just work on the homework and make sure you're comfortable about doing these multiplications and addition, subtraction, scalar stuff, the transpose things, and then after that, those are the basic tools to get us into more of the theoretical stuff. All right, let's go to chapter or section 2.2 where we start talking about inverses. And the idea behind the inverse of a matrix is that we're looking at what's called the multiplicative inverse of a matrix. And that's the additive inverse. If you look at the relationship between multiplicative and additive inverse. Additive inverse is to something that you add to a matrix to get what they're calling the additive identity. And the additive identity for matrices, just like real numbers, is 0, but it's 0 matrix. And so the additive inverse is what we know of as the opposite. So the inverse is, I think, too general of a name, but when they say inverse here, they actually mean multiplicative inverse. And for you to address the multiplicative inverse, you need to know the multiplicative identity. And the multiplicative identity was brought up in one of those properties. It's denoted by I, and then they have a subscript to say n to tell you the size of the matrix. But it's generally whatever size it is. It's a square matrix, same number of rows as column. And this is a matrix that has ones in its diagonal and zeros everywhere else, depending on how big it is. So if it's a 2 by 2, then you just have 1, 0, 0, 1 as your identity matrix. And again, they use the word identity and drop the word multiplicative. But when they're talking about inverses and identities in matrices, we're talking about multiplicative because the additive identity and the additive inverse is obvious already. And multiplicative identity or multiplicative inverse requires a little bit of work for us. And so we're going to study multiplicative inverses, also known as just plain regular inverses. So we'll start off with a definition, or a bunch of terms in our definition here, but invertible inverse are the basic ideas. And we'll use the term invertible. An n by n matrix is invertible if there exists another matrix. Right now we'll temporarily call it C, but there's going to be notation for it. C, so that C times A and A times C are both equal to the identity matrix. And if C is the inverse, then we can denote the inverse by A with a -1 power. So be careful that in matrix algebra, we don't have a division. We don't have a division process. And so you can't write something where you have a matrix in the denominator of an expression because that just doesn't make sense. Yes? Yeah, so C in this case would turn to A to the -1. Yeah. You can never divide by a matrix. Yeah. You can't have a scalar divided by a matrix either. Because we don't, there's no formal process for dividing a matrix. We can multiply them, yeah. So the multiplication was kind of defined in a certain way here. That's how we do multiplication. But then division, that's a little bit more complicated, a lot more complicated. And there's a lot of, there's restrictions, and we have to know if the matrix is, well, the next couple of vocabulary words there are singular or non-singular. So a matrix is singular. It could be a matrix of zeros, but it could be a matrix that's not full of zeros, but still it's a singular matrix, which means we can't find an inverse for it. And so this whole division thing gets a lot more complicated. So we just say we're not going to divide. Yeah, you can multiply it by, but that's not necessarily the inverse. And chances are you can't just take inverses of, each component and then expect to get the identity when we multiply. It still might not work, so it's a little bit trickier than that. Yes. So if you have a matrix, if I give you a matrix, so now you have this matrix. If you can find another matrix that you can multiply that by so that you get the identity, then you've found the inverse. And if you can't find anything to multiply that by to get the identity, then there's probably no identity, so it's called singular. So that's why there's a big study in this in matrices is to try to figure out what the inverse is, because sometimes we're interested in finding the inverse. Why would be why would we be interested in finding the inverse? I don't know. Well, why? Why ask why? Remember this equation? Yeah. So if we have we're interested in solving for x, right? So if we have the inverse, then we could just multiply the inverse times the b vector, and then that's going to give us our solution. And not only that, but if I have 15 different b's that I want to solve for, instead of doing row reducing for each one, I could just find the inverse and then do this multiplication 15 times, and then that would be easier than row reducing 15 times. No, it's all going to be hard. All right, so that's just one reason for wanting to find the inverse. Aside from that, there's a lot of other implications when we're dealing with vectors and linear combinations of vectors with inverses. You can check for linear independence if you can find inverses and things like that. So, I guess an interesting exercise to do. I just give you the formula, but I think we should try to do this and see if we can derive the formula. Um, and if you had some sort of pre-calculus that went really far in their advanced classes, and you might have seen this before. But suppose you had a generic 2 by 2 matrix, and generic 2 by 2 matrix, which means probably would mean we can make up random numbers for each of those 4 places in a 2 by 2 matrix. So we'll just call it A, B, C, D. If we have a generic 2 by 2 matrix, we want to know what to multiply this by so that we're going to get the identity matrix. So we're interested in figuring out what should these numbers equal so that we get the identity matrix. So let's say we know A, B, C, D. How we're going to find the other values? Let's say W, X, Y, Z. So we want to find values for W, X, Y, Z that would give us a 1, 0, 0, 1 if we multiply this. And this should go both ways. And we won't check that, but this should be W, X, Y, Z A, B, C, D. Should also equal to the identity, because that's one of the things they say. We're not guaranteed that if we switch the order of multiplication that it's going to be equal to the original. So we want to make sure that that's true too. I don't know if we'll check for that, but let's see. Let's do the matrix multiplication. So AB times WY. So in the first component of my matrix multiplication, if we do this matrix multiplication, should be equal to, so AW plus BY. And then AX plus BZ, and then CW plus DY, and then CX plus DZ. Now we're interested in solving for W, X, Y, and Z, right? We're assuming that we know A, B, C, and D. And this we want to be equal to the identity matrix, which means the first component has to equal a 1. And I'm going to stretch this out to make it look like a system of linear equations. We have AX plus BZ is equal to 0. We have CW plus DY equal to 0. And CX plus DZ is equal to 1. And then somehow we need to solve for stuff. I suppose we can put this into a matrix and then do should we do that? Or should we try to solve for it using just substitutions? We might be able to do either. I don't know, I haven't done this in a while. Well, let's be safe. Let's do the matrix. Let's get the matrix out of this. And the matrix looks like if W, X, Y, and Z are the variables, we have A, 0, B, 0, and then our augmented portion is 1. And then 0, A, 0, B, 0, C, 0, D, 0, 0, and 0, C, 0, D, 1. So we want to solve for this. It looks like we can get rid of, maybe we should have done it the other way. Should we divide by A first so that we have a 1? So 1 over A in the first row, and then I'll leave the C here because I'm going to knock that out, but I'm going to do 1 over A for the second row as well. So I have 1, 0, B over A, 0, 1 over A. 0, 1, 0, B over A, and 0. All right. So now with a couple of, I'm running out of room here. I'm going to multiply the first row by negative C. And add it to row 3. So multiply that by negative C. Well, let me write this down first. So multiply that by negative C, that would go away. There's 0 there, so there's no contribution. So this is B C over A plus D. Ooh. B C over A. Wait, it's negative. Negative BC over A plus D. 0, and then negative C over A. Yeah? Did that happen? Okay. And then I'll do the same thing over here. Negative C times row 2, add to row 4. So 0, and now this is going to become 0, 0, and we're going to get the same expression over here. And then we're going to get a 1 over here at the end. So this is minus BC over A added to D. It might have been good to have rewritten this. Maybe we can rewrite this as minus BC over A plus D. Common denominators, A over A. So minus BC plus AD over A. Yeah. So that's the same thing for this, right? Both of those expressions are the same. So I want to make those into a 1. So I think we can take the reciprocal. Right? Multiply by the reciprocal. So I'm going to take the third row and multiply by the reciprocal of this. I'm going to say this is going to be multiplied by A, and then I'll put AD minus BC. So the negatives there. And I'll do the same thing for row 4. So the first row stays the same. 1, 0, B over A, 0, 1 over A. Second row stays the same. So the third row, I need to multiply it by A over AD minus BC. That would make that third component equal to 1. Now I have a 0 here, but the last one I have to multiply that by this. Oh, the A's would cancel, right? Then I just have a negative C. Negative C over AD plus AD minus BC. And then I'll do the same for the last one. I have a 1 in there. Is that just A? Is that right? Yeah, A over AD minus BC. So it looks like we got this AD minus BC here as a theme. All right, so we got a couple more things to get rid of here. We want to make those zeros. I mean, we can back solve from here, but let's just make everything here zeros just to finish up our result. It looks like, let me work with the last row first. I could take row 4, multiply this by negative B over A. So I'll take row 4, multiply it by negative B over A, and add it to row 2. And then I'll take the same thing. I think it'll be the same thing, minus b over a times row 3 added to row 1. So in this case, that came from here, which came from here. We multiplied this by a over negative c over a times a over ad minus bc. All right, let's try the second row. I have 0, 1, 0, and this is going to become 0. But now what actually happened here? I needed to multiply the fourth row. This is a over ad minus bc. I needed to multiply that by negative b over a. So the a's would cancel, and then I have a negative b. Same denominator. And then my third component in my first row will also disappear because I'm getting rid of that from the third row. And then I'm going to multiply that by negative b over a also. So if I multiply that by negative b over a, I need to multiply this what am I multiplying? Row 3 by negative b over a. So I need a little bit more room. Maybe I'll put it over here. So I have minus b over a times a over ad minus bc, and then I have to add that to 1 over a. Right? Oh, how am I going to do that? I think I need a common denominator. So there's an a here already. I was going to cancel the a's, but it looks like we want to leave that here. And then multiply this by ad minus bc, ad minus bc, common denominators. And then I would have the same common denominator. And then the numerator would be minus ab plus ad minus bc. Is that right? Okay, what were we doing again? We're multiplying minus b over a. Oh, sorry, I need to do R3, row 3. So I need to do this thing. So this should be a minus c, right? So BC, negative, negative, so that's a positive. Oh, so the BCs and the BCs would cancel. In the numerators. And then the A's would cancel. Oh, there we go. And then we just have a D. Wow. So what does that mean? That means our first variable here is W, our second variable is X, and our third variable is Y, and our last variable is Z. So it would be D, negative B, negative C, and A. So it looks like W, X, Y, Z will equal to D over AB minus AD minus BC minus C over AD minus BC minus B over AD minus BC, and then A over AD minus BC. And this is supposed to be the inverse of ABCD. And I'll put the inverse notation of that. So, does this look familiar to people? Have people seen this before? Yeah. 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 So, that really difficult arithmetical process we went through gives us the inverse of any 2 by 2 matrix. And the inverse of any 2 by 2 matrix is going to be given by 1 over the AD minus BC times the matrix D, yeah. So this AD minus BC, I don't know if you guys are familiar with that, but that's called the determinant, and determinant of a 2 by 2 matrix is if you take a look at A, B, C, D, if you take a look at these two things as the what we call the diagonal, and these two guys are called the wings. It's the diagonals minus the wings is the determinant. And furthermore, the following matrix, after you divide by the diagonals minus the wings, is that you switch the diagonals and you negative the wings. So diagonals minus the wings, diags minus wings, and in here you switch the diagonal, negative the wings. So that's a quick way of getting the determinant of a 2 by 2 matrix. And so when I say, I was saying earlier that you can't divide by a matrix. Are we dividing by a matrix here? The determinant AD minus BC is a scalar. So it's okay to divide by a scalar, except when the scalar is equal to 0, right? And so if the determinant is equal to 0, then the matrix is singular. Did I say that here? So let's say it here. Yeah, so it's a quick way to check for 2 by 2s at least, because we know how to take determinants of a 2 by 2 matrix. But if the determinant is 0, then there's no inverse. Yes. The determinant's a little bit more difficult. Yeah, but that would be probably the easiest way to check if something is invertible. That, yeah, I know, calculator.
Knowing the determinant formula in advance.
Yeah, so there's no quick, easy way. Even finding the determinant formula, there's no quick, easy way to find a determinant. But if you can find a determinant of 5 by 5 matrix, then you can tell whether the matrix is singular or not. For a 3 by 3, yeah, but for 5 by 5, that's more more complicated. So for a 2 by 2 matrix, diagonals and wings, switch diagonals negative the wings, determinant diagonals minus the wings, etc. Okay? Inverses. So I mentioned this earlier. Why would finding the inverse be important? So it just turned out to be one of the theorems that you have in the book. I don't know if we need to say anything more. But the properties of inverses are interesting. I have a bunch of examples. So the first one, if A is invertible, then the inverse is invertible, and the inverse of the inverse is itself. Seems obvious, but needed to be said. The second one is not so obvious, especially because of the fact that matrices are not necessarily commutative. It turns out that if you have two invertible matrix A and B, and if you multiply them, you're going to get another matrix. The inverse of a product of a matrix is actually the product of the inverses, but the product of the inverses multiplied in the reverse way. So AB inverse is equal to B inverse times A inverse. Say it again. Yeah, the transpose, we saw last time that that's how the transpose worked. And so this also works for inverses. Yeah. Where's the B? The second one? Um, no, it's totally different from the transpose, but they happen to have the same property. Yeah. And then the last one, the inverse of a transpose is a transpose of the inverse. So you can take those two operations kind of interchangeably. I have a bunch of examples that you guys could try. I don't know if you want to. Um, let's try. Let's try a couple of them. All right. Let's change one of them to C and D. And so I'm going to point and have you try to do something. You do A times B, and you find A inverse, and then you find B inverse, and then you find A inverse times B inverse. So you have to multiply it. You have to wait till these guys are done and then get their inverses and multiply them. And then you do B inverse times A inverse. Sure. All right, let's go in the back over there. You do C times D, and you do D times C, D times C, and you do you find C inverse, and Jake, you find D inverse. Alex, when they're done, you multiply them C inverse times D inverse, and Nate, you go D inverse times C inverse. How about you guys in the middle? 1, 2, 3, 4. Oh, wait, that wasn't complete. So, Luis, you get Ali's answer and you find the inverse of that. You find Randall's answer and get the inverse of that. Andrew, you doing anything yet? You find Shem, raise your hand. You find his answer and take the inverse of that. And Raphael? No. Oh. Christian, you find Pedro's answer and get the inverse of that. You just check everybody's work to make sure it's right. All right, let's see, 5 minutes or something. Because you guys have to wait for them, huh? All right, so find whoever you need information from, get it, and then write it. And Matt's answer, right? Yeah. And then Alan's going to do the same thing, except he's doing it in separate order. You're going to do what Erica's doing, except in a different order. Yeah. And did you get his answer already? Oh. Yeah, you get her answer, which is still a 2 by 2 matrix, I hope. And then you find the inverse of that. Telephone? It's not, though, because that telephone, you make a mistake, right? These guys are not going to make mistakes. Yeah, but the longer the string is, you're going to distort something. So the people that are taking the determinant, right? It's 1 over the determinant, or people that are taking the inverse, 1 over the determinant times the flip the diagonals, negative the wings. No, you're finding the inverse of the product. He's taking the product. Is that what you're doing? You took the product of AB, and you're supposed to take the product of BA. I messed this one up, didn't I? What are you doing? B inverse. Oh, so I wanted BA. Okay, is anybody doing B times A? Sorry. Good luck. I mean, Erica's doing that too. Doing the product of a bunch of fractions. Yeah, but you're whining. Wait, say it again. AB. Can you do BA also? What? I don't know what that means either. I don't know what's going on anymore. It's just finish your work and then I'll make something up. Which one are you supposed to do? You're out? Okay. All right, we'll see. All right. So yeah, it is. Well, I'm not denying it. All right. So the idea here was that you're supposed to find your partner. I don't know what that means. Well, Ali is gonna have. Wait, no, Luis is gonna have some partner, but I don't know what happened in the back because I think I lost track of things. All right, let's see if you guys got what you're supposed to get. Oh, you're not done? Okay. All right, well, what I wanted to get at, because it probably didn't happen, is that I wanted somebody to do A times B, and then I wanted somebody to find the inverse of that, and then I wanted people to find B inverse, and an A inverse, and then multiply that and show that they're actually equal to each other. So Luis and Alan should have the same answer.
Yes. Alright. There's maybe one over 9 in there.
Okay, so it must be correct. I don't, sorry, I messed this one up. But that was the idea. So I have a couple of, I mean, I can just give the answers. And then I wanted to do the switch, B times A, and then A times B were supposed to match up. But I think I forgot to do B times A in these calculations. Mathematica simplifies my fractions, so I got 1 over 270 for one of them, and then the rest are whatever the rest are. But I think the common fraction would probably be the determinant, which is negative 14 times 40 minus 20 or something, which is probably, I don't know, 540 or something. Does that seem right? Okay. Anyways, negative 540 is the determinant. Okay. All right, so let me just put one result of this exercise that totally bombed. It's all fun and games until the professor doesn't know what he's talking about. The A times B is equal. Did you get this, Ali? No? Oh. Okay. Well, um, all right, let's move on. let's forget this ever happened. Yeah, I could just accidentally delete today's lecture. Or you can go back to this lecture and play at half the speed and then. So, anyways, what if I just leave it up to you to practice taking inverses, multiplying matrices, and stuff like that?
Put the left side as the original matrix and augment it with the identity matrix.
Yeah, but we'll say that for higher dimension matrices, because the inverse of a 2 by 2 is just 1 over the determinant. That's a lot easier to deal with. But that would be an algorithm for later on. But let's introduce ourselves to this thing called elementary matrices. An elementary matrix is a matrix that you get when you take an identity matrix and then you perform one of the elementary operations. There are 3 elementary operations, if I remember correctly, right? What are they? So you multiply one row, add to the other one is a switch, and then the other one is a scale. So you're just scaling a row, right? So it's interesting that if we take an elementary matrix, so an elementary matrix would be, let's see, the identity matrix is it takes an identity and then it does something to it. Like let's say we're switching, let's switch the rows. So I'm going to call that E1. So if you take the identity and you switch the rows, then this is called an elementary matrix. The interesting thing about an elementary matrix matrix form is that if you take a matrix like this and then we multiply this matrix by an elementary matrix on the left side, what do you think is going to happen? It's like doing that switch on the matrix, right? Does that make sense? If we multiply your identity matrix let's say E2 is equal to, let's say we multiply the first row of the identity matrix by 5. So this is the identity matrix, and we multiplied the first row by 5. Let's see what happens if we multiply the same matrix A with this elementary matrix. So the matrix A, remember, is -2, -2, -4, and 5, right? So we multiplied this matrix by by 5, 0, 0, 1, and so it does the same thing. And let's do it. Let's do one more. Let's take the matrix A, or let's take let's do a third elementary row operation on the identity. And what we'll do is we'll multiply the first row by -2 and add it to the second row. Oops. So I take the identity matrix and multiply the first row by -2 and add it to the second row, and this is what I get. So now let's see what happens if we multiply the matrix A. This is the matrix A again. What happens if we multiply the matrix A, the first row, by -2 and add it to the second row? We should get a 0 down here, right? So let's see if that's going to happen. So it turns out that whatever you do with this elementary matrix, if you multiply a matrix A on the left side by this elementary matrix, then that elementary matrix is going to do to that matrix what you would normally do in a regular row operation. Okay? If I guess it says here, because I forgot what I said. An elementary row operation performed in an m by m matrix is the same thing as multiplying that matrix by an elementary matrix that does the same thing. So this whole idea, if you have a matrix A, B, C, D, and then you do a row switch, R1 switch with R2, and then you get C, D, A, B, right? Well, if you start off with the identity and then you switch the rows, this is an elementary matrix. So elementary matrix. And what this elementary matrix is a row switch of your identity. Then if you multiply this by A, B, C, D, then you're going to get the same thing as if you had done the elementary row operation on that matrix. Yes. So whatever you want to do with this matrix, you can first do on the elementary matrix, on the identity, and then multiply it on the left side. If I want to get rid of A in my next step, I would probably multiply this by negative C over A or something like that. You can do this on singular matrices also. So the last paragraph here says that each elementary matrix is invertible, and the inverse is going to be the same type of matrix. So if I take my identity element or my identity matrix here and I switch the rows, how do I get it back to the original identity? I switch the rows again, right? And I get back to the original identity. Okay? All right, it's 2 o'clock, so we should be done. Practice the algebra, the matrix algebra, because there's a lot more information about inverses that we need to get through.